Welcome. In this video, we will cover the content for Chapter 13, which will be the chemistry of the air. Earth's atmosphere can be divided up into the four major regions. The region that's closest to Earth is the troposphere. This is the layer of the atmosphere that covers Earth's surface and includes all living things. In this figure, we have on the x-axis the temperature, and on the y-axis the altitude in kilometers. You can see this blue line represents the temperature as it increases based off of the altitude. In the case of the troposphere, the temperature will decrease as altitude increases. The troposphere ranges from 0 to 10 kilometers. Once we hit around a little past 10 kilometers, the stratosphere begins. In the stratosphere, temperature will no longer decrease with increased altitude. At this point, we see that the temperature actually starts to increase again as we get further away from the Earth's surface. The ozone layer is also contained within the stratosphere. The layer above the stratosphere is the mesosphere, and then the outmost two layers of the atmosphere are the thermosphere and exosphere. Most of the chemistry that we're going to talk about in this chapter is within the troposphere or the stratosphere. The air is composed of a variety of different chemicals. Here we'll go over some of the most abundant chemicals that are found within the air. And the air we're looking at here is clean, dry air near sea level. Roughly 78% of the air is composed of nitrogen and 21% oxygen. The other 1% is mostly argon. There are a variety of trace substances and carbon dioxide that compose the last 1% of the air. Nitrogen gas is the most abundant gas in the atmosphere. Nitrogen gas has the formula N2. This gas is relatively inert, and it can't react to form new molecules very easily. In order for organisms to use nitrogen, the nitrogen first must be fixed or combined with other types of atoms to form new compounds. There are a variety of different ways that nitrogen can be fixed, and we will learn about them throughout this chapter. The first way that nitrogen can be fixed is through the following reaction. One molecule of nitrogen reacts with one molecule of oxygen and uses the energy from lightning to form the new bonds in nitrogen monoxide. This is a pretty interesting reaction because the nitrogen is so inert that it needs the energy from lightning to break the nitrogen-nitrogen bond in order to form new bonds. If you recall, when we discussed acids and bases, nitrogen monoxide is an acid anhydride. Nitrogen monoxide can also react with oxygen to form nitrogen dioxide. Nitrogen dioxide was also listed as an anhydride. Nitrogen dioxide is an acid anhydride which can react with water to form nitric acid. This is what that reaction looks like. Three molecules of nitrogen dioxide react with one molecule of water to form two molecules of nitric acid and one molecule of nitrogen monoxide. This can lead to the nitrogen in the atmosphere reacting to form acid anhydrides, which can form acids in the atmosphere. These acids can contribute to acid rain and slowly acidify the oceans and soil. It also acidifies the lakes and streams. While lightning can fix nitrogen naturally, we have also developed an artificial process to fix nitrogen called the Haber-Bosch process. In this process, one atom of nitrogen reacts with three atoms of hydrogen gas to form two ammonias. This process is used on large scale to produce ammonia for the increased productivity of soil and food production utilizing fertilizers. Naturally, nitrogen can also be fixed by certain plants containing bacteria in their roots. The nitrogen cycle represents the flow of nitrogen through the atmosphere, the seas, and the land. Atmospheric nitrogen can be fixed and form new bonds with different atoms in a variety of processes, both in the atmosphere, forming nitrogen dioxide and nitrogen monoxide, through bacterial fixation, and then through industrial fixation in the Haber-Bosch process. Bacteria can decompose some of these molecules and release nitrogen gas as a byproduct, which can circle back into the atmosphere. The other major contributor to the composition of the atmosphere is oxygen. Oxygen makes up roughly 21% of the Earth's atmosphere and has its own cycle shown here. In the troposphere, oxygen is converted back and forth from carbon dioxide through the processes of respiration and photosynthesis. In the stratosphere, the oxygen can mix and react with the energy and UV rays from the sun to form ozone. This ozone forms a screen above the atmosphere, which we'll discuss in more detail later. In the stratosphere, oxygen can absorb UV radiation to form ozone, and ozone itself is capable of absorbing more UV radiation and reflecting some of the heat off of Earth.